Hello, people. I hope everything is okay on your side and you can hear me well. Um, I'm going. I will try to be quick today because we have important stuff to discuss, and I want you to see a lot of stuff today. So last week we opened up this discussion about set associative mapping um, in caches, obviously, and okay, remember that also last week we took this example, right? This um, hypothetical program consisting of just three instructions. Uh, the instructions are these, right? With these hypothetical codes, each instruction being placed to um, a given address that we considered. So I'm going to take the same example, right? Only this time, just a second to take my tablet. It's a big one, so I need two hands to do that. So um, I'm going to take the same example. Only this time, we will consider. So it's the same example as last week. Just come on, work for me, right? So this is example 2, maybe. If we take the same thing, I mean the same conditions, namely um, these conditions, right? So mm, look, I'm gonna take this, right? Right? Okay. So we are talking about the same example. It's just that this time um, the same size of the main memory. A word is one block for words. Um, but this time we don't have direct mapping. This time we have two-way associative mapping, right? Because we are talking about two-way about set associative mapping, right? Okay, so that's we are talking about. That's what we are talking about right now. The size is everything is the same. Now, I'm not going to draw the main memory again because I draw it last week for the first example, for the example with direct mapping. And that would suffice, obviously, because the structure of the main memory is not changing. The only thing that changes is the structure of the cache. Now, about the cache, right? So let's draw it. So this is the cache. It has two banks because because it's a two-way set of associative cache that has two banks of memory, right? Um, and the index, right? One index works for both these banks. So this is bank 0 and this is bank 1. Okay, so right? It goes this way, like this, right? Something like this, okay? You have a valid tag, bit, like this, and the data, data, tag, okay, and this is the valid bit. Okay, so just draw it like this. Okay, right? This is valid tag data. Okay. So, is this? I mean, we are talking about the same. So this is the address word, right? So the size of the main memory is the same. Therefore, the number of bits in the address and the addressable unit is the same as in the first example. So the address was on 24 bits. So this address is the same on the same number of bits. So it's on 24 bits. 2 bits are used for the offset, you know, like here, right? So we have the word offset, right? It's the same thing on 2 bits. Word offset. Now, the size, um, the size of the cache, the data set size of the cache is 1 kilo block. This means 1,024 blocks, right? But these blocks are now divided into two banks because with one index, at one index, I have 2 blocks. So it's divided by 2. Therefore, the index goes from 0 to 511, which is 2 to the power of 9, obviously. So you divide right the cache size by the set associativity, and this is 2 to the power of 10 blocks, right? And you divide it by set associativity, which is 2 to the power of 1 is 2. So this is 2 to the power 9, and this 9 gives the index, the number of bits in the index of the cache. Okay, good. Actually, this is m is 10 and s is 1. And remember from last week that the index is on m prime bits, which is m minus s, namely 9 in our case. Now, let's go further and right. So we have from 2 to 11, right? Sorry, 10. We are talking about 9 bits over here. So this is in the index. And the tag, right? So it's 24 minus 11, that's 13 on 13 bits. Okay, so what we do right now is that, okay, we have the same program, right? So we have this address, which is at this instruction from address, and of course, data is also like last week is on 4 blocks, on 4 words. One block is on 4 words. So this is block. This is word 3, or word 0. Sorry, word 1, word 2, word 3. 4 words, right? Like this, like this. Word 0, word 1, word 2, word 3. And the valid, as we know, is on 1 bit. The tag is on 13 bits, right? And one word is on 8 bits. So we are talking about a total of 32 bits. 4 times 8, that's 32, right? One word is on 8 bit. Now, as I said, the first address is where we take the first instruction is this one, which is 2 to 13. So it's 8192. Yeah, 92. Oh, sorry. This is stupid. So our address is something like this. So it's to the power 13, that's 14, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and the rest are zeros, right? This is the address, right? So these 2 bits are the word offset. Then the index is on 9 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is, right? The index is, right? The index is 0, and the tag is 6, right? So it's 4. Sorry, it's 4. So this 200 and the code, right? 230 will be put in the cache here, right? 230, 1, 2, 3, and so on. Right, 0, 1, 2, 511. Okay, and we have a 4 over here. And this, well, it doesn't matter. We do not care about the content of the other words in the block, at least in our problem here. Now, the instruction from the next address is 2 to the power. So it's the address is this one, which is right, 96 plus 4, which is 2 to the power 12 plus 2 to the power 2. So it's something like this, right? 2 to the power 12, right? Plus 4. Right? So the index would be 1, and the tag is 2. So, right, this is valid, this is valid. We put, what is the code? 2715. 2715, we put it here, okay? Right, so this is how we place it in the cache. Now, so this is 4100. The last address, which is this one, so it's 12292, right? So 12,292, when we subtract 8,192, we have 0, 0, 1, and 4. And we know already this guy. So it's 2 to the power 13. So this guy is 2 to the power 13 plus 2 to the power 12 plus 4. So it's 0, 0, and so on. 1, 1, 0, right? 0, 0, 0, 0, 0, 0, 0, 0, 1, and
David
0,
Buzet has said it's 12,922, not 12,292.
So what do you say? Yeah. 292. 200. Yeah. 292. Yeah. 292. That's correct. 292. So yeah. 200. That was the only mistake over here, right? Here it is correct, and here here the same. Yeah, the same. So yeah, this is the place where it wasn't correct. So okay, the index is 1, but we have index 1, so index 1 is occupied here, but now we have the possibility of putting 2 blocks at the same index, and that is why I can put it here in the entire block, which contains this address. I can put it in the cache, and I'm going to put it here at index 1, obviously, because the index is 1. The tag is 6. Oh, sorry. The tag is 6, just that I didn't put it where it belongs, here. And the contents of this block is 170 here, the hypothetical code 170, and whatever. It doesn't matter what for our problem. So that's what it works. And in this example, you can clearly see why set associative is a little bit better in dealing with this situation where your program, your software involves many blocks, and when you have direct mapping, some of these blocks will kick each other toes from the cache. I mean, we'll kick each other out of the cache actually, because these blocks are mapping at the same index. But with this solution, you can have different blocks at the same index, right? Because you have a set of blocks associated to that index. So that was the idea. Okay, the most, when you have a set associative mapping, and that is section 312. Let's talk about 313. There is obviously, if you have okay, let me give the title of this section, which is full associative mapping. Okay, so you see, everything is a set associative mapping actually, because you can see you can consider direct mapping as a special case of full associative mapping, namely k is 1, right? When k is 1, you have direct mapping, right? It means that you have one block for one index. And of course, k is 2 to the power s, and s is 0 in this case, in the case of for direct mapping. Now, the next case is the another extreme case. It is the case where k is 2 to the power m, or in other words, s is m. Well, in this case, all the blocks in the cache are associated to the same index. Actually, you don't have an index anymore because it's just one. So you are not obligated to distinguish between indexes as long as it's only one index. So you don't have an index, right? So all the blocks in the cache are the same. They don't have an index. The only way you can identify blocks in the cache is by comparing tags. It is therefore this solution is the most compliant with the locality principle. So it it reduces a lot of cache misses because of the locality principle. If you have a big enough set associativity, or even more, if you have full associativity, it means that you're very compliant with the locality principle, and you reduce the number of misses to the minimum. However, this solution is not that good in terms of performance because, okay, you win in terms um, um, of misses, reducing the number of misses. But on the other hand, the cache uh, access time is actually bigger. Why? Because searching in the cache becomes very difficult. Searching after tags is a difficult job, and searching sequentially is out of the question. If you have a big enough cache, it means that you take sequentially, I don't know how many, thousands of blocks and thousands of tags, and comparing them sequentially, that is out of the question. So you need to implement a solution that is based on parallel searching, meaning associative memories and stuff like that, which is very, very expensive. So this solution is not that scalable, right? So it's very good, but you need to come up with a very sophisticated way of searching these tags, and it's not scalable, right? Um, when the cache is small, you can think about implementing it in as a full associative cache. Now, coming back to our example with the block numbers, right? When for M2, meaning the main memory, n is 5, and you have something like this, right? From block 0 to all the way to block 31, because you have 32 blocks, and you have block 12 over here. Right? Now, and you have the tag, obviously. Sorry, this is not the tag. Um, is the cache for M3. But this means that this that is like this because you have come on. You have something like this, right? Again, maybe my drawing is not very good because these blocks are equal, that. So, but this is not obvious from my drawing. I'm sorry about that. right? So, and this is the data part and the tag part, all right? Something like this, okay? Um, you can put it just anywhere, okay? For instance, I can put it here if I want to, or I don't know, something forces me to do so, I can put it here. But again, I can put it just anywhere. And just look at the, if I don't have an index, look at the address, right? It's on 5 bits because block number is on 5 bits. So it's 01100. You have no index, right? So the size of the index is 0. So this address this block number, sorry, is the actual tag. You know, so the tag for full associative caches is actually the block number, right? So it's 01100, right? I put the tag, the corresponding tag over here. And if we take the example, let's take the example, our example, with the three hypothetical um, instructions at those addresses. So our cache would be something like this, right? So you have only one bank. If the cache is initially empty, I mean, I can put here some numbers, but these numbers are not used, right? I put numbers here only for you to see that the cache has 1 kilo blocks, right? Meaning 1024 blocks, 1024. And this is the tag, right? This is the valid. Again, this is the tag, the valid. Okay, and the data. The data is again on 32 bits. It's the same. The valid is on 1 bit. Now let's see the tag. All right. Now the tag is on how many? Because I don't have the index. Is on 22 bits. So the address would be the address would be something like this, right? So you have 0, 1. This is the word offset. That's on 2 bits, and the tag would be on 22 bits, right? From 2 to 23. Okay, good. Now, coming back to these addresses again, and I'm not going to write them because it's useless. Now this time the tag will be for this address, right? The tag would be, right, this quantity, which is, this would be the tag for full associative tag. The tag is equal with this guy divided by 4, right? So it's this value divided by 4, actually, because you take these two zeros and the entire, rest is the tag. So is 40 and 92. Sorry, divided by 4, not by 2. Sorry. So it's, come on. So this is 2048. And here right? This would be the tag, okay? And this is for full associative, the tag is going to be so this guy would be 1024 plus 1, so this is 1025. And here, the tag would be this quantity. So this quantity is this one plus this one, right? So it would be for full for full associative, right? The tag, which is the actually again, I say I will say this again. This is the block number, so it's 3073. Okay, good. Now here, when the processor executes the first instruction, I'll have one. The tag would be um, as, as computed here, 2048, right? And the data, of course, the four words, 230, and don't care, don't care, don't care. And then, the next instruction with code 2715, don't care, don't care, don't care. And then 3073 with the hypothetical code over here, and don't care, don't care, don't care. Okay, so that's how it would look like. Now, in what follows, I'm going to, give you an example. I will take um, uh, I don't know how to put it. Um, Bigger or stronger example. I don't know. Um, I will. I also wanted to take an example from Patterson and Hennessy's book, but I will take from the top of my head right now. I will take an example. So this would be example 4. So we consider a computer system where the main memory size would be 4 gigabytes. Okay, that's the size of the main memory. In such a system, the addressable unit is the byte, right? So each and every byte has to have um, a distinct address. One word would be on 4 bytes. Okay, one block would be on 8 words, and the cache is 4-way set associative. Okay, and the cache data size is um, uh, I don't know, 16 kilobytes. Okay. Now, what we need to do is to find the address word format, Okay, B, find the total cache size. We will see about that in just a few seconds. And C, the cache logic diagram. Now let's address the first point A. Now, how many bits in the address? That's the first question, and it's a very simple question because we know that each byte has a distinct address, and we know how many bytes are in the main memory. So 4 gigabyte, again, the byte being the addressable unit. This means 2 to the power 2, that's 4, and 1 giga is 2 to the power 30 bytes. Right? So this is 2 to the power 32 bytes, which means that our address is on 32 bits. That's the address word size. Okay? Okay. Now, coming back to our offsets, right? So one word has 2 to the power 2 bytes, and therefore 2 is the size of the byte offset, right? That field that identifies each byte in a word, and one block is on 2 to the power 3 words, which means that obviously this is the size of the word offset. Good. Now let's see the index. Well, for the index, we need to analyze the cache size. So we have 16 kilobytes cache size, cache data size, which is 2 to the power 4 times 2 to the power 10, because 2 to the power 10 is 1 kilo, 16 is 2 to the power 4 bytes, is 2 to the power 14 bytes. That's the size of the cache. Now, I'm going to divide this size to the size of one block. But how many bytes has one block? Well, one block has 2 to the power 3 words multiplied with 2 to the power 2 bytes per word, right? So in total, I have 2 to the power 5 bytes per block. So when I have this quantity, I can see that when I'm doing 2 to the power 14 bytes per cache and divided by 2 to the power 5 bytes per block, right? I will have 2 to the power 9 blocks, right, per cache. Right, so the size, this is the size of the cache data size in blocks. expressed as a number of blocks, not as a number of bytes, right? So that many blocks. Now, on the other hand, 4 blocks are associated to one index. That this means that I have 4 memory banks. Therefore, I will have to divide 2 to the power 9 blocks per cache to the power 9. I said 9 and I wrote 2. Yeah. To the power 2 blocks per index. And that is because of this is the set associativity, right? This is the set associativity. This guy is S, right? And the whole thing, right? This 4 is K. Good. Now, when I divide this, I get 2 to the power 7, and that is blocks per bank. And 1 block is 1 cache line. So this 7 is the index size. Okay. So right now I have the answer. Why? Because the tag obviously is what remains. So the address word will look like this. So I have from 0 to 31. So this is the address word. Okay. I will finish here with point A. So this is the byte offset on 2 bits. This is the word offset on 3 bits. Something like this. Maybe it's not proportional. It would not be very proportional, but nonetheless. Okay, let's. Okay. So this is the index on 7 bits, and the rest. The rest is 10, 12 out of 32. So this is 20, right? That's the tag. Okay, so let's answer to point B. All right. So at each, I have 2 to the power 2 banks. That's the set associativity. Times, right now I'm calculating the size, the total size of the cache, right? Times the 2 to the power 7, and these are blocks, right? Blocks per bank, right? Times, and in each block, and each, or cache lines, blocks per bank or cache lines per bank, and it is the same thing. In each cache line, I have now let's talk about data, right? So I have 2 to the power 3, and these are words, right? Times 2 to the power 2. These are bytes, and I'm going to put it as such here, plus, now the tag is 20 plus 1, so it's 21 bits. 1 bit as or let's put it like this: bits This is the tag, right? Plus 1 bit. This is the valid bit. Okay, so it would be like this, right? So it is simple for me to just, you know, split this parenthesis, what's within the parenthesis, as bits and bytes. Let's compute the bytes, right? So it's 2 to the power 9 times 2 to the power 3 and 2, that's 2 to the power 5 bytes, plus 2 to the power 9 times 21 bits. So this would be 2 to the power 14, 2 to the power 14, that's 16 kilobytes, right? Now let's see about this, you know, supplementary part. And I want to, you know, to approximate this as a number of kilobytes. Obviously, because I want to add this quantity to this one, and this one is expressed as kilobytes. Obviously, here I cannot, this is not a power of 2, so I cannot express it as a number of kilobytes. So I'm going to, you know, um, approximate this, and you always approximate a little bit up. So the, you know, most accurate approximation upwards is when you approximate this quantity as an even number. Why? Because you need to divide it by 2. Because 2 times 2 to the power of 9, it means 2 to the power 10, and that's 1 kilo. So this is approximated as, this is not approximated 16 kilobyte, but this one is approximate 2 to the power 9 times 22 bits. Okay, and this is approximate, this is 16 kilobytes plus 2 to the power 9 times 2 times 11 bits. Oh, these are bits. So yeah, two, let's put it like this. So yeah, so I 2, it's 16, yeah, 24. The best approximation is 24. Let's not uh, um, lose time, too much time. Why? Because this is 2 times um, um, no, 32. Sorry about that. This is 32. 32. We need this to be a multiple of, to be bigger than 22, and a multiple of not only 8 but 16. If I'm putting this as 16 times 2, yeah, I mean it's, yeah, it's 2. It has to be a multiple of 16. So times 32 bits. So this is, it goes like this. This is 2 to the power of 5 bits. So it's 2 to the power of 2 times 2 to the power of 3. And these are bits. Okay, these are bits. And one such guy, to the power of 3 bits, that's 1 byte. So this is 16 kilobytes plus this is 1 byte. This is 2 kilobytes. So again, it is approximately 18 kilobytes. Okay. It is somewhere between 17 and 18 kilobytes, but yeah, that's um, an upper bound estimation. Okay, so this is the estimation of the total cache size. Now let's see about a logic diagram of the cache. And we have something like this. Okay, we have the address word, right? So we have 0, 1, 2, 3, 4, 5. This is the byte offset. 2. This is the word offset by 3. This is the index, which is the index is on 7 bits. Okay. And this is the tag on 20. We have something like this. Okay, I'm going to use this copy thing. No. I'll stick it. Like this. Okay. I'm going to put it right here. And again, here, and again, here. Something like this. Okay. So, yeah, I was stupid enough not to do this for, yeah, nonetheless. Okay. This is the valid. This is the tag. And I guess the tag is on 20 bits, right? And this is the data. How many bits? So I have 8 2 to the power 3 times 2 to the power 2 bytes. That's 2 to the power 5 bytes. So it's 32 bytes. But in terms of bits, 2 to the power 5 times 2 to the power 3 bits, 2 to the power 8 bits, and this means 256 bits. Now, I have indexes from 0 to 127 because it's from 0 to the power 7 minus 1, and so on, right? Okay, so let's do this same way. This, 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 this. I'm not going to write it again here. So, one, this. Mm, you get the idea, right? Okay. Something like this, right? This is the bank 0, right? This is the bank 1. This is the bank 2. And this is the bank 3. Now, with the index, I'm selecting, right, the corresponding blocks out of these 4 banks. And then we compare this, right? This equal sign means a comparison with these bits from the tag. Okay. Something like this. Okay. Like this. Okay, so it compares with, okay, like this. Okay. 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 And then you validate this with the valid bit. This. Okay. This. Okay. Now, this. Okay. And like this. Okay. We have an AND gate here as well. Okay. So you need to, use these because you only have one here. You may have all zeros here when the information, the block is not present, the desired block not present in the cache, or you may have a one hot situation when only one of the blocks is the block that this where the word that the CPU needs is. Okay, so I'm gonna need here a multiplexer 4 to 1, right? And to this end, I have, you know, I have these bits, these bundles of, 256 bits, right? The entire block going here as well as here, right? Oh, I missed the first one. Jesus. Oh, okay. So okay, let's put it like this. Um, what do we have here? Um, it's time to no. Yeah. The problem is that I put this stupid multiplexer over here, and actually it should be put here. Uh, just a second, like this. So 4-to-1 multiplexer. Okay. Yeah. So this goes over here, and this guy goes over here as well. Right? 256 bits. And this guy goes over here. Again, 256 bits. Now, these bits are going here as selection bits, as well as here, right? That's one bit, right? One bit, selection bit. And these guys also this guy goes here. Okay, this guy goes here as well. As a selection bit. Now, let me make this drawing nicer. It's supposed to be nicer, but okay, like this. Okay. Now you have here, right? It selects the block on 256. The corresponding block, the block that corresponds to the selection line where is a 1, and then you have a 8x1 multiplexer which selects one of the 8 words, right? And there you have on 32-bit word that the processor needs to read. And to this end, I need the selection of these things. Okay, Okay, so yeah, that's the complete picture of this example cache, an example that I think is quite compelling, and it brings um, enough stuff for you, so that you can understand how this cache actually works. So okay, let's exit from here. Um, I want to bring another example to the table, and that is um, another you know problem or exercise, or you name it. Um, so this is, or example, I don't know, example 5. Okay, so this example sounds like this. Um, a cache um, of, of, um, of, well, we have a system which contains a cache that is four-way set associative. Okay. Um, this cache has 8 blocks per bank and 4 words per block. In this cache, one word is 1 byte. Okay. The size of the main memory, so M2 size, is 2 to the power 16 words. Okay. But this is right. I said that one word is 1 byte, so it's 2 to the power 16 bytes, which means that it's 2 to the power 6 times 2 to the power 10 bytes. So it's 64. That's to the power 6 kilobytes, right? Of course, this is a very small main memory. It's just an example, right? It's a hypothetical example, such that we will understand a lot of stuff, as you will see in just a few. The addressable unit, of course, is the word, but it's the byte at the same time as the byte, because one word is 1 byte. The cache is initially empty. And the cache access time is 20 nanoseconds. The time required for moving 4 words what happens? Oh my god. Time required for moving forwards, and that is a block, right? Moving one block between the main memory and the cache. We will see that this is called miss penalty. And this miss penalty is, as I didn't say, it's 500 nanoseconds. We consider LRU, we will see what this means, policy. for the cache. And we are asked to A, present the memory address format of this cache. That's point A. B, compute the hit ratio. When this computer system will execute a program that is given as a sequence of instructions, knowing that one instruction is on one word and one word is 1 byte. So the code of the instruction is on 8 bits. It's on 1 byte. Okay, again, this is a very simple example that was valid only for very, very old generations of computer systems. But nonetheless, if we want to understand the mechanism behind it, we have to do this. We have to reduce sizes because that's it makes it simple for us to follow things. If we take modern examples, it would be impossible to follow things on a piece of paper or on a when we write on a board or something like that. So that's the idea. Okay, so one word is 1 byte. 1 byte is one instruction. And I give the sequence of instruction as the sequence of the addresses where such instructions are to be found. So these are not the codes of the instructions. The codes of the instructions are irrelevant in our case. We only consider these addresses. So we start with the instruction at address 30, then 31, then 32, and so on and so forth, up to address 160. Now, when it gets to this address, we have a conditional branch, which means that it will jump at address 105 and execute it 5 times. Okay? So, starts here, 30, 31, 32, 105, 160. Oh, conditional branch. Some condition is tested and jumps 5 times at 105, and then it goes, sequentially to 160 again. And then from 160, it goes to 161 when the last loop is completed, up to 170. Okay, and here it stops. So in such a for such a program, we are asked what is the hit ratio. And point C, for the program that we consider at point B, what is the average memory access time of the cache? I will present you and I will make clear each and every such thing and idea here. Now, let's start with point A. We know that the total memory size is 64 kilobytes. It means that we have to have 2 to the power of 16 distinct addresses, which means that the address word is on 16 bits. Obviously, we don't have a byte offset. Why? Because one word is 1 byte, meaning that we have 2 to the power 0 bytes, right, for one word. So this 0 is the size of byte offset, right? Instead, we have um, a, word offset. Why? Because we have um, uh, oh, I didn't say this. Oh, I said it. Yeah, it's just that. So I have 4 words per block, 2 to the power 2 words per block, which means that this guy is, right, this is the size of, of the um, word offset, right? So this guy is 2, and then I have the index. Now, let's see about the index. Well, not too much to say about the index because we are told that we have 8 blocks per bank, and that is the index. How many indexes, right, per bank? Meaning we have 8 lines of cash per bank. So this is 2 to the power 3 blocks per bank, right? Meaning that this is 3 is the index size. Okay, so we have 2, 3, 4, and this is the index on 3 bits. So 11 bits are for the tag. Okay, so that's how we answered to point A. Now for point B, I need, maybe you will find this as annoying or boring at first, but let's do this. So I have an address 3D address and block number. Okay, and this is the main memory, M2, if you wish. Um, so okay, we have something like this. Of course, we have 4 words per block, and each word is in fact 1 byte, and each one has its own address. So I'll have 4 addresses for 1 block. For instance, here from 0 to 3, that's block 0. Okay, from 4 to 7, block 1. 8, 11, 12, 15, and so on. 16, 19, 20, 23, 24, 27, 28, 31, 32, 35, 36, 39, 40, 43, 44, 47, 48, 51, 52, 55, and continuing, 56, 59, 60, 63, 64, 67, 68, 71, 72, 75, 76, 79, Um, yeah. So this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. Now, let's see. Right, this is the address, this is the block number. Now, oh my God, stuff like this. This is so stupid. 80, 83, 84, 87, 88, 91, 92, 95, 96, 99, 100, 103, 104, 107, 108, 111, 112, 115, 116, 119, 119, 120, 123, 124, 127, 128, 131, 132, 135, 136, 139, 140, 143, 144, 147, 148, 151, 152, 155, 156, 159, 160, 163, 164, 167, 168, 171. And here we stop because the last address, I mean, the address of the last instruction is 170. Now, these blocks are 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, and 42. Now, let's see about the cache blocks, right? So this is about the cache blocks. Okay, this is 0, 1, 2, 3, 4, 5, 6, and 7. You have the valid, the tag, and the date. Okay, valid, tag, data. Okay, now I'm going to this Okay. Okay, I'm going to put it here. Okay. Hmm. This is so stupid. Nonetheless. Okay, good. It- it's still stupid, but you get the idea. Okay, so um this is the cache. This is the cache. 1, 2, 3, 4. This is bank 0, bank 1, bank 2, and bank 3. Now, I am the processor, and I need to read the first instruction of the program. That instruction is at address 30. Now, the first thing where I'm looking when I'm trying to read something is the cache. And for some reason, this stupid idiot has taken all these. Okay, it's good now. So it needs the instruction from address 30. Is the instruction in the cache? I mean, the word from address 30. Is it in the cache? Of course not, because the cache is initially empty. So all these valid bits are 0. So the this first access, memory access from the processor will be a miss. Okay, but when it is a miss, the processor will read the word from the main memory, namely 30, and 30 is in here in this block number 7. And as we already discussed, when something is not in the cache controller will bring that word, but not the individual word, the entire block that comes with this word. In our case, block number 7. Now, where is block number 7 going to be put? Well, you do this. 7 modulo the number of indexes, right? So it's 8. 7 modulo 8, and that is 7, right? So I'm going to put it, right? So this is block number. Block number is 7. Okay, when you write it, and I'm going to write it here, right? So we have 7, right? So we are talking about these. We are not talking about the word offset. Block number. So you take the last 3 bits. So when you have 7, is 0, 0, whatever, 0, 7, right? And then, yeah, that's the block number. Block number. Block number. Okay, because we are talking about the block number, because the block number is given by these bits. We take only the last 3. Okay, so this is the index, which is clear. It's 7, and this is the tag. So when the first access comes, as I said, it's one miss, because 30, the word at address 30 is not in the cache, but at the same time, with this miss, we bring the entire block. So we bring the block here, 1. The tag will be 0. No, not here. In bank 0. Sorry. Here. So it's 1, is 0. And we bring, okay, we don't know the contents of these words, but we know we will represent them as the addresses from which we take these contents. So it's 0 from address, sorry, not 0, 30, not 30, 28 to 31, right? Is this one? 28, 28, 28 to 31. Okay, so 30 is a miss, but then the processor wants to execute the instruction from address 31, but that instruction is here in the cache. Why? Because we brought it with the block. So it's 1 miss and 1 hit. And then the processor needs 32. But 32 is not there because the cache is empty. And, well, it's not all empty, but 32 is in block 8, which maps, because 8 is like this. 8, the block number is like this, right? So that's how 0, 1, 0, 0, 0. That's 8. Okay, this is the block number 8. Number, this is 7, this is 8. So it's 8, which means that it maps at index 0, and the tag is 1. Actually, if you think about it, you can easily obtain the index by doing this, right? And the tag is the quotient of the division. When you do 7 divided by 8, the quotient is 0, and the remainder is 7. That's why 7 modulo 8 is 7. Okay? So it's 0 in integer. And that is the tag. Now, the tag for 8 modulo 8 is 0, but 8 divided by 8 is 1. So the tag is 1. So the processor needs 32, and it's not there, but it brings it here at index 0. The tag is 1, and there you have it, 32 through 35. So 32 is a miss, obviously, but the next instructions from 32, 30, 33, 34, and 35, these are all hits because they are already in the cache. You see, 33, 34, 35 are there. And it's the same thing for the next blocks. And the next words which the processor needs. So from 36 to 39, it's the same. Valid, the tag is here. And then you can see that this is block 9. 9 modulo 8 is 1, so the index is 1, and so on and so forth. 40, 43, 44, 47, right? 48, 49. Sorry, 71, 51, 52. I said 52, and I wrote something entirely different. So it's 52, 55, and 56, 59, 60, 60 to 63 is here. 60 to 63, you see, it's block number 15. Modulo 8, that's 7, and the quotient is 1, so is 1 here. Now, then 64, 67, you see, 64, 67, that's at block number 16, modulo 8, that's 0. So it maps at index 0, but 16 divided by 8, that's 2, so the tag is 2, and so on, right? 68, 71, 72, 75, 76, 79, 80, 83, 84, 87, 88, 91, then 92, 95, and then 96, 99. See it here, 96, that's 24. Divided by 8, well, it's 0. The modulo is 0, so it maps at index 0, but the quotient is 3. So 100, 103, 104, 107, 108, 111, 112, 115, 116, 119, 120, 123, 124, 127, and then 128, 131, and this is 24, 27, all right, 28, 31, that's 32 divided by 8, so modulo is 0, this time the tag is 4, right, and so on. 131, sorry, 32, 32, 35, 36, 39, 40, 43, 44, 47, 48, 51. Now, what happened here? Oh my god, this is so stupid. Yeah. Oh, don't tell me. I knew I shouldn't rely on such shitty software as Microsoft. This is so stupid. Jesus. Okay. Luckily, I didn't lost it again. So, okay, so 140, 143, 144, 147, 148, 151, 100. Don't make me. Don't tell me. This is so stupid. And now the cache is full. But the processor needs the instruction at address. But let's stop for a second. So for all these blocks that we bring, we have this correspondent. One miss, that's, well, for the instruction from the first word of the block. And then the last three in the block are put in the cache along with the first one. And they are there when the access from the processor comes. So it's one miss and then three hits. Now, how many times did we have this? Well, with the exception of this block, which was put here at index 7 in bank 0 at first, which was one miss, one hit, the other blocks, meaning 31 of them, so that's times 31, were one miss and then three hits. And now let's continue. So we go here. Okay, so okay, so we are at 155, right? So the processor needs 156. This guy obviously is not in the cache, although the cache is full. 156 is in 39, right? So 39 modulo 8, because it is a miss, right? So 156 is a miss. It's a miss, one miss, right? So it will bring it where? So this is, right, modulo 8, that's 7, right? And 39 divided by 8, that's 4, because it's 4 by 8 that's 32, and the remainder is 7. So I'll put it at index 7. Now, that's where this policy least recently used comes in play, because I need to throw something out of the cache, right? It's a competition between this block, this block, this block, and this block. Who is going to be thrown out? Well, according to the locality principle, that's only reasonable to throw out the block that was the least recently used. And it is the case of this one. So this will be thrown out, and I'm going to bring here 156 through 159. The tag is 4, as already computed, and that's what we'll do. And then we need 100, and that's in itself, it means one miss, 156, but 157, 8, and 9, these are 3 hits. And then we have 160, and that is a miss. When the processor needs 160, why? 160 isn't here, obviously. Where is 160? Well, it's in block, here in this block 40. 40 modulo 8, that's 0, and 40 divided by 8, that's 5, obviously. So it will, it's a competition between these guys now at index 0. Who is going to be thrown out? Well, the least recently used, obviously, again, which is start normally, you stupid idiot. Okay, so as I said here, okay, one miss, that's 116, because I'm bringing here 160 to 163, and here I have 5 as tag. Now that's just one miss. Okay, so and then if we are looking at this program, then it jumps at 105 and executes 105 through 160 5 times. Now, if you look closely to all these words here, the words from addresses 105 through 160 are all within the cache. So how many? So from 105 to 160, this means, right, 56 instructions, right? So it is 56 accesses, and all are hits, okay? All are hits. So, and that is time 5, because 5 times we execute 105 through 160. So it's 56, and it's 5 times, and this is 30 and 28, right? So it's 0 misses and 280 hits. Okay, and then after these 5 loops, okay, it doesn't jump anymore at 105, but the processor will execute 161. But 161 is in the cache, right? It's here in this block. So it's 161. That's one hit. 62, 2 hits. 63, 3 hits. So it's 100. These 61, 62, 63 are all hits. So we are also counting 0 misses, 3 hits. This is beginning to be a nightmare. This is last time I am using this stupid, moronic one note. It needs to clean something. I guess so. So it's 0 misses, 3 hits.
David Busitis said maybe it's because the streaming eats a lot of RAM.
Yeah, I know, but I don't want to bother too much with these stupid details. Um, Damn it! Sorry for this takes too much time for the wrong reasons actually. So it's 3 hits, and then let's move fast. Okay, so 106. I lost the track. Let's move to paint. I don't know. I don't know what to do. Damn it! Let's try one more time. Sorry for taking your time with this stupid thing that happens, but let's hope that this time it will work. Okay, so I guess this is 1 miss and 3 hits, and then it's 1 miss, right? 1 miss, 0 hits, and that is for 160, right? 160, that's 5 over here, 163. And then we have these from 105 to 160, that's 65. Sorry, it's 56 times 5, because it's 5 times, so it's 33, 25 plus 3, 28. So it's 0 misses. Sorry, guys, I don't know what to do. I don't know what to do. It's the first time this. Okay, guys, look what I'm going to do. I'm going to, end this stream for now, and come back in I don't know, in 5 minutes after I restart my
David Buzet
computer.
has said here it's a print screen. David Buzet has said try it in Paint.
Okay,
and
yeah.
then start again.
Thank you very much. Yeah, thank you. Now something very stupid happens here. Okay, I'm going. I will come back in 5 minutes.